Hey everyone, welcome back to another AP Calculus video where we're going to explore more related rates. And today's problem of the day is the shadow problem. And the shadow problem is a typical problem that has shown up on AP exams in years past. And usually the one that people are most familiar with, you'll probably see this in an AP classroom, is the man walking toward or away from a lamppost. And the question asks about how fast his shadow is changing. And it's a great problem, and it involves similar shapes and similar triangles, and it's just a great problem. And so this is a similar problem that uses a lot of that same thinking. So let's take a look. And remember, our steps to solving a related rates problem are always the same. Draw a picture, write down what we know, figure out what we want to know and write that down, write an equation relating all of our variables, differentiate that equation with respect to time, and then solve for that unknown. So let's draw our picture. We have a man 6 feet tall walking toward a building. So here's my building. It's a very disproportionate building. We're going to have a tall building and kind of this tallish man. And then it says he's walking towards, there's a light on the ground 50 feet. So we've got this light shining on him, this spotlight here on the ground. And it's shining this light and it's causing his shadow to appear on the building, right? So here's his shadow on the building, and we want to know if he's walking towards the building at a rate of 5 feet per second, how fast is the man's shadow getting shorter? Because as he walks towards the building, that shadow will get smaller and smaller. How fast is it shrinking when he's 30 feet from the building? So let's fill in a couple of things that we know. Remember, the only numbers that go into our picture are numbers that are constant. So one of the constant numbers is that this light is 50 feet away. That's one of my constants. The other constant I have is that the man is 6 feet tall. That's not going to change. The other things are going to change, his distance from the building, because he's moving. So let's see if we can kind of understand what's happening here. As this light shines on this man, it creates a triangle. And you might be thinking to yourself, oh, it's a right triangle. I should use some sort of Pythagorean theorem. And that's a great thought, and I'm glad your brain is going that way. In this particular case, it's not going to be helpful, because in order to use the Pythagorean theorem, we would need to know two sides and a hypotenuse. We don't know anything about the hypotenuse. So let's write down what we want to know, or what we do know. We know that the distance the man is walking towards the building is changing at a rate of 5 feet per second. And there's a little typo there, don't mind that. So I need to label this. So I'm going to label this distance x. So whatever distance the man is from the building, I'm going to call it x, okay? That means dx dt is changing at a rate of -5 feet per second. So that's a value that I know. Then it says, how fast is the man's shadow on the building getting shorter? So I need to figure out this distance here, and I'm going to call it y. I don't like calling the shadow s because it looks too much like the number 5. So I try never to use the letter s if I can avoid it. So I want to know dy dt when x equals 30 feet. That's what I want. So now I need to write an equation that's going to relate everything so that I can solve that equation. And like I said, the Pythagorean theorem is a great idea, but it's not what we want here. What we want to notice, though, is that we have more than one triangle happening. So I'm going to draw the two triangles in. We've got this yellow triangle from the light with a fixed side, and then we have this green triangle. And this green triangle is going to change as the man walks forward. And I'm going to draw a little arrow for the man also, because I like to remember that he's walking this way. And notice dx dt is a negative value because x is getting smaller. Negative rates imply that we're getting smaller in our value. So let's see if we can understand some things. So if Pythagorean theorem is not the way to go, maybe we need to think about these two triangles as being similar shapes. And when we have similar geometric shapes, similar shapes have proportional sides have proportional dimensions. So anything that's a corresponding side or a corresponding part, so hypotenuse to hypotenuse, leg to leg, corresponding parts of similar triangles are proportional. That's some long geometric, you know, with all the letters and stuff, CPTC. I can never remember. There's a reason why I've never taught geometry, and while I love geometry and it's wonderful, I can never remember all the letters. But I remember the concepts, and so that's all we need here is corresponding parts of similar triangles are going to be proportional. And so this means we can set up a proportion. But before we do, I need to figure out this little green side, and I need to realize that if I know that this distance from the building to the man is x, this distance here in my little green triangle is going to be 50 minus x. So I need to know something about both sides, and so I'm going to use the y and the height of the man. Those are my corresponding parts. So let me color code those. So this side and the height of the man are corresponding. And then this side and the long length are corresponding. So the equation that I'm going to write is going to involve a proportion that I set up. So here we go. 6 is to y, so I'm going to put the little one on top, as 50 minus x is 250. So now I need to realize when I go back and I look at all I know, all I want to know, do I have the information I need to be able to solve what's happening? And I know that I'm going to have a y in my equation, or a dy dt. I know that I'm going to have a dx dt. There's a chance that I might have an x. That's a possibility. But this is the proportion that I'm going to set up and that I'm going to need to solve in order to answer this question. Now, I'm going to run into some trouble when I start differentiating with respect to time. Let's see if you can figure out where I'm going to run into trouble. So to differentiate this equation, I'm going to rewrite this as 6y to the negative 1. And then I'm going to go ahead and do my derivative. I'm actually going to simplify this right-hand side also, and I'm going to put each term over 50, and I'm going to make this 1 minus x over 50. The more I can make something look like a polynomial when I'm doing a derivative, the easier it's going to be on me. So now this derivative ends up being negative 6 over y squared equals, this turns into negative 1 over 50. And I'm going to throw my dx dt and my dy dt in. Now, my job, once I've differentiated with respect to time, is to go back and plug everything in. And you'll notice I have a y, a dy dt, and a dx dt. And up here, what I want is dy dt. I have a dx dt, and I have an x value. X is 30. But in my equation, I have a y. And I'm curious, did you see that that was going to happen? I need to figure out what y is. So sometimes we differentiate, and when we go to plug in the values that we have, we realize we're missing something. Well, my promise to you is this. If it's a well-written related rates problem, you'll always have everything you need in the problem to solve and be able to find the answer. You just might have to think about it a little bit longer and do a little bit of work to get that information. So let's return to our original proportion here, and let's see if we can set some things up. We know that 6 over y is the same as 50 minus x over 50. So if x is 30, we want to know what y will be when x is 30. So what I'm going to do is I'm going to solve for that. I'm going to say 6 over y equals 50 minus 30 over 50. So I have to get that y value to be able to plug it in later on. So this becomes 20 over 50. I get 6 over y equals 2/5. And ultimately I get y equals, 2 over 5. So when I multiply everything together and find my y value, I end up with y is 15. So now I have that missing piece of information. I'm going to go back to where I started from, and I'm going to plug some things in. So negative 6 over 15 squared equals negative 150, oh, and I have my dy dt, equals negative 1 over 50 times dx dt, that was negative 5. And now I'm going to do some solving and find dy dt. So after a little bit of arithmetic, we end up with our answer, negative 3.75, or negative 225 over 60. You can leave it as an unreduced fraction, that's fine. But we're always going to include the units, feet per second. So let's make sure that our answer makes sense, right? So if I go back up to the shadow, and as he's approaching the building, the shadow should be getting smaller. So I expect a negative rate of change, and I have that. And does it make sense that it would be shrinking by about 3 to 4 feet per second, so 1/1000? Yeah, if he's taking steps and he's going at a reasonable pace, that light is far enough away that that shadow will shrink very quickly as he takes steps forward. So is our answer reasonable? Always a question that you should be asking at the end of every word problem. So again, this was a proportional reasoning problem. We had to go back and find a value for y, because when we did our differentiation with respect to time, we didn't have a value for y, and sometimes that's going to happen, and it's quite all right to get to that point. And so maybe you saw that moving forward and you realized you needed to find y. If you didn't, don't worry, you'll get there and you'll realize, oh shoot, I don't have anything for y, and you can always go back like we did and find it. So again, negative 3.75 feet per second was our answer here, and this is one of those triangle problems that you're not going to use the Pythagorean theorem for. You're going to use a proportion to relate those similar triangles. So always remember that these problems may seem tricky at first, and they are kind of tricky. But don't get discouraged. The more you practice, the more of them that you do, the more, the easier it becomes to pick out the information and to see, oh, this is one of those. So there's different types of problems that you're going to encounter, and this is just one of those types, and it's a proportional ratio type problem. So keep practicing. You can do this. You're going to get there. You've got this.